Hello everyone and welcome to another live stream. Made it in time. I don't have anything, so that
2 minutes to spare.
It wasn't even close. Come on, it was easy. Alright, I need to share on Discord as well. Change everything. I love the... I absolutely love the... you mind if I start the stream right now because I need to start it right now. No one's joined in yet, so...
It's because you started it before you even pinged.
I had to. It's no time to spare.
People are going to start asking what VC you're in.
The most exclusive one. Hi Ashad, hi. Welcome.
How long did you say the thing's going to take?
I mean, you can see that it's actually uploaded already. Everything... YouTube is checking it, but they should be down checking in 5 minutes.
Exciting.
Yeah. I set up the schedule for in 15 minutes. So he is on time. Hi, the Catman. See, y'all were just worrying over nothing. It wasn't even close. Did YouTube check it? I think they did. Hi, Ditha. Hi. Make it, would like to read a 3,000 character opening into a intro to a story I'm writing. On the YouTube chat? I'm often on Discord. I'm pretty certain we even have a channel for projects. I would love to read that. By the way, Flame, because I do understand that you would have to go, so if you need to go, just let me know.
Oh, it's fine. We planned it for like in 20 minutes.
What's up, and today we may explain the deal with the Hilbert spaces. Yes, we may, Reblax. I have time today. Hey, you won't believe... Remember that video I was working on yesterday so you could... it's finished, finally. About goddamn time. 2 weeks in. That's good. Why is it invisible on YouTube? Oh no, it is. There we go. The photoelectron spectroscopy is just great. The thumb that love that thumbnail. Honestly, might be top 10 thumbnails I've ever made.
What do you think of this this pin comment?
The person's out, yeah.
Will it delete it if it's got the Discord link?
I don't think they should, especially since you have mod.
Let's try.
Yeah. It's fine with zombie, it's fine. I'm not gonna, as I mentioned, you were doing me a favor. I'm not gonna be upset just because you didn't do something that I would, like, didn't do some voluntary work that I wouldn't even pay you for. How dare you! These unpaid interns. I really need to dock their pay. But yeah, by the way, everyone wondering, the video.
My comment?
Yes, just give me a sec. Need to restart, refresh the thing. Is the comment right there? Hiking love photo electrons. Hell yeah. There we go. The pin. I'm even gonna give you a heart. You're welcome. I actually didn't read the comment. You've actually changed it in the meantime. It just says make it sucks or something. By the way, there is one last thing I do before I upload videos, or usually during uploads or like after, whatever. And it's my favorite part of the video making process. Or actually, it's like a ritual where basically I get to weigh in the video and decide where it goes on the top 16. Would you like to join me in this, Flame? deciding where the video should go in the top 16 Make It videos. Okay, flame is muted. Alright, wait, where Make It? Non-live VC. Not yet, Roblox. Not yet. I'm still finishing up the video thing. You see my earlier version of YouTube? Good shot for a second. Oh, hold on. There's no actual chat.
I was muted. I was going to say sure, but I'm entirely unbiased here.
I was actually about to say I would love your completely unbiased view.
Someone's already asked what that machine is in the live chat preview.
Wacky mysterious machine. Alright, there's definitely above the logic ones, definitely above these, above all the chemistry, let's do physics, above this chemistry, above white acids, above the energy one. I think I'm gonna put it right here, place number 7. And I am removing the building computers for that. There we go. Sacrifice has been made. Video. The contraption, the thing that does the thing, you know, the thing. I wonder what it does actually. The thumbnail is so mysterious on this topic actually. I don't understand. How am I supposed to understand this? Any of this? Mickey, we are so close to 6,000 subs. This video, I would just like to mention. Oh, that was a really quick train of thought. I switched from how many subscribers we're missing to how many subscribers I'm going to get into the video itself. But the thing is, this video will either get 2,000 views or like 80 or 90,000. I don't know which one will it be. I don't know if it will be like the typical YouTube video, hyper-specific YouTube video that does nothing. You know, that only
hyper-specific.
Yeah, exactly. Or if it will be like a Richard Bechiel talking about spinners or something, where it just makes a video about spinners, which is just as hyper-specific.
That video
it gets a million
like
views.
Yeah.
It's gonna be what, like, this is
that is literally one of my favorite videos. It's in my, I don't like many videos, but that is one of them.
I do have to say, will either be this video or this video. Which is funny because the superconductivity one, that's like 4-5 times as long.
I don't know what it is that's so appealing about the spinners one.
I think because it's just it is very confusing. It combines all the worst, like the most confusing parts of mathematics with spinning, which is the most confusing part of physics.
For me, I just watched it because I thought it would help me understand spin, and it didn't. I need to watch it again though. I think I fell asleep halfway through. Well, I was in bed. I put it on and I think I fell asleep.
I mean, I get that. It is a very long video. And so I do imagine that most people who were watching the video were just watching it late at night because that just seems like a target demographic. I need to make a video about spin of Remco. You're gonna explain everything shortly. Can you switch to the live chat, by the way?
I can see it now.
Live chat like the Discord.
What do you mean?
Like on the Discord channel, the live chat, the voice chat for lives.
I'll have a look.
Well, there we go. Joined in here.
Oh, I thought you said, "Can you see the live chat?" Not can you switch to.
Okay.
I was like, what chat is he talking about?
Yeah, I don't know. That's just my
and
pronunciation.
then you disappeared. I'm like, oh, he didn't switch to.
Oh yeah, you know, that's just my pronunciation. You know, I say filing instead of firing. It's how things are.
Filing lasers.
I'm gonna be mentally scarred for the rest of my life because of this. I just want you to know that.
Someone is gonna comment filing lasers.
Yeah, and I'm gonna just have a complete mental breakdown. I'm laughing now, but on the inside, it's just empty. Completely empty. How's it going, Make It? Actually, surprisingly good paper. I finished the video. Flame.
Yeah, it only took 2 weeks.
It's exactly over 2 weeks. It's fine.
It's a good thing these videos only depend on you and not on some other person who's busy with things.
I mean, to be fair, like, I had complete control. I could have just, after 4 days, also work on the quantum field theory video. It was, I don't want to blame you for it, because like it was my decision to just solely focus on this one, and it was a bad decision. I should have just spent work on the quantum field theory as the main, because then we wouldn't have to rush this either. Which, to be fair, we didn't really rush it, did we?
No.
Despite, this was the most careful video I have ever made on my entire channel. No other video got this much attention. Which, I mean, I know that your standards might be a bit higher, Flame, but my standards are such that this is the most careful video that's ever been on my channel.
Which one?
The most recent.
Like our one?
Yeah.
Huh. I mean, it makes sense. I was also very, like, picky about...
Yeah, the thing is...
I'm really... You've discovered how perfectionist I can be.
I have... Yeah.
Now you understand why why I had to pull that 24-hour thesis, whatever.
Busy, should I go and write a section in the chat later on? I will read in a second, Ashad, but Ashad, you've joined. It's a bad time right now. In like a half an hour, it's gonna be a good time, but right now it's a bad time because the video is up, and that's a big deal. It took me 2 weeks to make the animations for it. It's a lot. Are we doing a math stream? Actually, this will be a walk stream. I am going to rest today by just walking on the math video. That is how I plan to spend my rest time.
Yes, that sounds very restful.
It's a fun script. I like it. Also, you know.
After a long day of quantum mechanics, I always love sitting down and reading quantum mechanics.
I'm honestly excited to just not walk on. I don't have anything against this video. I just
research.
No. I just am really excited to work on anything else.
Anything else?
I have that at the end of every video. That's kind of the main force pushing me. Like, I hate every
Like,
single
you get
video I
sick
make.
of it, yeah.
I get so sick a week in that I just need to switch, and then I realize that I need to finish the video to switch, and that's actually huge motivation. Man, hatred is such a powerful motivator. Ping me, let's go to start reading. I'll join the stream. Alright, the shot, alright. Oh, I haven't eaten anything. I made myself some pasta. I haven't eaten.
Didn't you make food? Did you burn it?
No, it's still there. I mean, I did, but on a non-stick pan, so it's fine. I can afford some carcinogens in my body. You know what? I think I have too little cancer, if anything. So that should do me some good.
I mean, if you ever want more, just come to the lab.
You just want to make my cancer glow. You don't want to fix anything. Don't pretend as if you actually. You just want to make it glow.
It's actually funny because that's literally what my summer thing was. It was literally making the cancer
Yeah,
glow.
I mean, no, you're trying to fix it.
So the objective was to make cancer glow. Oh, it's actually funny.
What time is it over there? It is the next day right now, but we started on the correct day. It's right after midnight. We did not, in fact, cut it close, and we did, in fact, get the stream on time. The human body can handle quite a lot of carcinogens. Yeah, but I have the pasta. I know. Let me actually bring it here. Some water as well would be nice. Wish I think I'm gonna kill myself. Think I'm gonna kill myself. Okay. I'm back-ish. And now I am.
Wait, can you hear me?
Yeah.
I'm gonna go now.
Alright.
But I'll watch the premiere. I'm gonna watch it with a friend.
Oh, bad idea. I mean, okay. I hope I uploaded the right video. Bye.
Bye.
And it's just a 10-hour loop of a seal spinning or something. Chemistry is cancer magic. As in, it's magic and it gives you cancer. Probably my favorite time of crackers from China, the controversy about having them thin layer of kenja juice. Yum! Is there a new video releasing soon? There is, in fact. In 5 minutes? 3 minutes? Have 60 seconds. Yes, exactly. I'm gonna ping it as well. Make it do a reaction stream. I don't want to watch. Listen, trust me. I've seen it. Made it. I've seen it. Trust me. Oh my goodness. I've been. I don't think you'll realize this is like the video. Okay, to be fair, I was also working on all the videos, and I do have a fair bit of animations, fair bit of scripting, fair bit of stuff done for the other videos. However, this is the video I've spent most of the time working on. This is what I devoted most of my attention to, and I've spent 2 weeks watching 20 minutes of it. Well, kind of like a week and a half watching 10 minutes, and then half a week watching another 10 minutes, but still, it's a lot, okay? I know this video. I love the thumbnail though, it's so hilarious. So dumb. Alright. Well, in the meantime, I need to take my mind off the video, so Reblax, you want to join, or are we doing something? Oh my goodness, I'm such an amazing cook. Oh my goodness. Gracious me. Oh, I'm phenomenal. Wow. That's delicious. That's incredible. Oh my goodness. Save some of us. I don't think I'll be able to. This is so delicious. Wow, I am incredible, truly. What did you make? Pasta with a sauce. Some onions, ground beef in there. And tomato thing. 11 herbs and spices. Some of them are even legal. Delicious. I thought about chucking garlic in there, but I was kind of working on the video when making this at the same time, so... The Italian pasta thing, exactly. Daddy chow, if you will. But to be fair, I am so hungry that I'm pretty certain I could just eat a block of cement and it would taste good. I'm biased. So, because Reblax isn't... Oh wait. Oh yeah, I was supposed to read Dishad's thing. Give me a second. Because Reblax ain't joining in. Absolute cinema. Oh, I should make the... Oh, hold on. I should make my own version of Make It saying Absolute Cinema, actually. Hi, Reblax. How you doing?
What's up, gamers? Reblax here.
We can finally figure out why the heck can Hilbert space do the inner product when the inner product requires a dual system with 2 Hilbert spaces.
It's like, I won't say it's easy because nothing in math is easy, but if you know vector spaces, it's not that far from what you know.
What I know about vectors, my understanding of a vector space is that it's a set with rules.
Yeah. And the rules
Yay!
make it look like vectors.
Yay!
Alright.
I know because I'm making a video about this, so now I'm at my peak understanding.
Right. I have some TI stole from the math department. But like, I'm allowed to steal it, so it's fine. We've got free tea and free coffee, make it. It's amazing.
Okay, I mean, what else is like your budget is gonna go for? Marcus.
Exactly. Yeah. All right. So, we're going to make some room here. Maybe let's move stuff.
Yeah, the
that's
rule
on
of the rule of the math whiteboard. No deleting. This already looks great. I like how with each, like, progressively I understand more and more of all the crazy writing. Like, for example, this. I don't think I understood it when you wrote it down, but now I understand what it means.
All right, great. We'll be important.
Oh, good.
All right, all right. So, like, maybe first let's define what an inner product is. So, start out simple. So, since we're going, I'm just gonna take like V as a vector space. So, vector space over R, I'm gonna say. Start. Also do vector spaces over C afterwards, because the physicists use them for quantum mechanics, so that may be of interest to you and other people.
Mm-hmm.
But now we use real numbers as scalars. All right, so the inner product is supposed to generalize the dot product that we already know. Like, that's the aim.
I see.
What's cool with the dot product? Well, it kind of tells you the angles between vectors. Like, you've got formula that has a cosine in it, so it's basically so it gives you angles. And the notion of inner product actually allows you to talk about angles between, well, abstract vectors. So that's nice. And also, the very important thing is that if you have a vector and you dot product it with itself, it gives you the size of the vector squared. And that's
So,
gonna be very important.
Square root of the dot product of a vector of itself gives you the norm.
Yeah, exactly. That's going to be like very important. So I'm just gonna say, like, the dot product. What's it? What's the dot product? It's just an operation that takes in two vectors and it spits out a number. So an inner product is going to be an operation that takes in two vectors and spits out a number. All right, so the math way of writing this would be like to do something like this. So V times V is actually like the product space. Basically, it's just here to say that we take two vectors as inputs.
Mm-hmm.
If you've done programming, maybe you've like written a function on couples of ordered pairs of things. Well, V times V is the set of ordered pairs of vectors. No, we don't want any function, because any function, like, it doesn't have anything to do with anything. We want stuff to be usually linear in linear algebra. But the dot product is not really linear. It's a little bit spicier than that. What do I mean? Well, basically, if you've got like lambda x plus mu y times lambda prime x, or I mean, I'm gonna put other vectors. There's a dot product here. Plus mu prime w. If you expand out the dot product, doesn't like, basically it's like a product. You have like the distributivity rules, basically. So what does it give you? It gives you lambda.
Yeah, reflex.
X times w, and so on and so forth. And my internet is a bit shaky, so that's going to be a problem.
Yeah, you did do the funny echo thing where you just set basically like that.
All right. Yeah. So I might disappear at times. It's not because I've been kidnapped by the math police or the physicists, for that matter. I'm fine. I am happy. I am not suicidal. feel like you should mention that.
I do worry about you from time to time.
I'm not
By-
Sayajal yet. I'm not a PhD student.
You need math-life balance.
Did you know there's actually a whole YouTube channel for this? It's not a joke. There's a mathematician and she has a YouTube channel called Math Life Balance.
I
And I'm
know.
actually going and I'm going to one of her talks in late June.
I do think
Anyways,
it's an important topic because I mean, as nice as evolution is, the whole killing off all the mathematicians we deem unnecessary thing by making them suicidal thing. It seems kind of like ethically dubious, at least. Oh no, his internet disconnected.
Yeah.
Right. Okay, there we go.
No, I'm still here. Right. So basically, like the thing we want is that we kind of want it to we want our inner product to be linear, but only if we fix one of the two inputs. I'm gonna write out what that means. It means that so that's
Intuitively, it
also
makes
called being
sense.
bilinear. Wait, use the comma. So we want this. We want this, and we also want something very similar to this, but in the other place, the other variable. So I'm just gonna do the famous trick that math professors do and move stuff around from the blackboard because that's allowed. Very practical. And so that's the part where it's important that we work over R, because over C, as you've seen, we ask for one of the two arguments to be anti-linear. So it's not really the same.
Mm-hmm. That makes
But
sense.
here we're over R, so everything is cool and normal and perfectly bilinear.
It's simple. It's simple, yeah. It's not that complex. It's mandatory, man.
Right.
They wouldn't. I need to.
Bilinear. All right. So yeah, that's the first important thing. The second important thing is that you want the dot product to not care about which vector comes first, because it measures an angle, like doesn't see whether it doesn't orient the angle basically. That's the intuition behind it.
Mm-hmm.
So we ask for x, comma y to be equal to y, comma x. That's called being symmetric for obvious reasons. Like it's symmetric.
Right.
And again, in C, it's not exactly symmetric. It's like conjugate symmetric. So you add a bar on top, complex conjugation on top. For reasons. I haven't really for some reason, you never exactly do inner products over C here. You just at some point, they just start showing up and you probably go frantically Google things to follow along. So I don't exactly have perfect intuition. I don't have a lot of reasons in memory to explain why stuff works like how it works over R. Anyways, the last thing. Wait, did I disconnect again?
On the middle of when you you came back with the over R, so.
Oh, right. Basically, this, the symmetry over C, it works differently. You have a complex conjugation,
Mhm.
but here we do everything over R. And the last thing that's very important is that we ask for the inner product to be positive definite. What does that mean? It means that if we do x inner product x, this must be greater than or equal to 0. And in fact, so that's positivity. And being definite is that we ask that if xx is equal to 0, well then x must actually be 0, like the 0 vector. Which makes some sort of sense. If the norm of a vector is 0, it's the 0 vector. Like, it can be any other. It can be any other one. Right. So that's just what an inner product is. That's like all there is to it.
Right.
Now, why do we care about inner products?
Get generalized way to get the norm.
Yeah. Basically, so like as an example, you can use like if you have Rn, so n-dimensional space, the dot product, which works in any dimension. Nothing weird going on here. Like it's just express stuff in a basis and you product the things, like it's the dot product. That's always an inner product space. But there's not just that. There's also other cool inner product spaces. For instance, if you do something that looks a lot more like what's done in quantum mechanics, if you do what's called L2 of R, so what is this? That's notation to mean functions f that go from R to R such that the integral from minus infinity to positive infinity of the absolute value of f squared is finite. So we call these functions square integrable because you can like square them and works out. There's actually like a whole lot of LP spaces, like you can change the exponents, but L2 is the nicest one because it's actually an inner product space. And what's the inner product? Well, the inner product is given by f and g. It's actually going to be the integral from minus infinity to positive infinity of f times g, so fg. It's just the multiplication. Maybe I write it out like it's f of t, g of t, dt. There's like one thing to check here. It's not obvious. It's that if f is square integrable and g is square integrable, then the product of the two is actually like just integrable. But it's true. It works. That's the sort of space they use in quantum mechanics because the wave function is a function, so it's complex valued, so it's over C, it's not over R, but the wave function is a function that's defined on like R if you do one-dimensional stuff, and you want the integral of the wave function over all the space, of the square of the wave function over all the space, or the square of the modulus, because we're over C. You want the integral of the square of the modulus of the wave function to be 1.
Yes. Normalized
Because
for probability reasons.
Yeah, exactly. So it's not exactly L2 because L2 doesn't care about what the value of the integral is, but I mean, it's this sort of space. And like the cool thing with inner products is that you can like just think of it as, well, an inner product space. It's an abstraction. It unifies some stuff. And there's not just that. There's also like you could, for instance, take polynomials. These make up a vector space, and you can do. And there's a lot of interesting inner products on those that give rise to a lot of important families of polynomials, which I don't know because I'm a fraud. It's not like a big thing, but it also exists, is what I'm saying, basically. All right, so like that's the first part of what makes inner products cool, is that they unify a lot of stuff. The second part I'm going to talk about it right now is because obviously you know I haven't defined a Hilbert space, because a Hilbert space must also be complete. And that's
Isn't
actually
that
another thing.
just like a
Yeah.
limit? That's like
Yeah,
a
yeah,
limit gives you.
Yeah, it's about limits. But basically, that's the thing. A vector space is just it's pure algebra. It's just a set with rules. There's no way to like take limits in a vector space. So you need some extra structure on it to take limits. And the inner product, it gives you that structure. How do you do that? Well, you turn it into a metric space. The distance is given by, so the distance between two vectors is going to be the norm of the difference of the vectors. And if you have an inner product, well, that's just the square root of
Inner product
x
of the
minus 1.
differences of each one.
Exactly. Why am I rating it like this? Well, because sometimes you don't have an inner product, but you still have norms. Normed vector spaces are also big. In fact, usually you at least have a norm because you just don't want just a random distance. You want something that's actually compatible with like addition and scaling
Yeah,
and
well,
stuff.
it makes sense the distance function to be set to norm that like checks out.
Yeah.
I would say.
I mean,
I
could,
know how.
I mean, it's so you could also make shit up and just like put a weird distance
Funny enough,
function
in
on
the
your space,
video,
but it's not really interesting.
in the video, I actually, in which I talk about, actually use as an example of a simple matrix space, just a literal space like a game with players, where there's players in different places. In which case, you could just get. Well, I use Pythagorean as an example, but it means the same thing. You just get norm of each one. But at the same time, if you were creating a different space where you just want to make like matchmaking between players, and you want to get two players with the closest skill level or closest power level or whatever, then you would probably define your distance function to be something more wacky, because I don't know, we could have like a space with attack, mana, and health, and you would like value health twice as much as attack or whatever, and then you would probably have a really wacky distance function, which wouldn't make intuitive sense. I think I'm with you so far. It's fishy because usually when it's a Reblax explanation time, I shouldn't be with you. That's the problem. Usually I get lost really quickly, so I'm suspicious of the fact that I don't feel lost yet.
It's because I'm going like quite.
Yeah, I mean, I can tell you're going.
You've already like I'm kind of tired, so I'm going slow for also my sake. And also like you've already looked into the stuff, so you're not like discovering it for the first time.
Yeah,
so that's helps. That obviously helps. But basically, what I meant is that, for instance, you can have really wacky metric spaces. Like a metric space is just a set with a distance function. It's not necessarily a vector space. In fact, it's In fact, like if you have some graph, you can put an interesting distance that computer people study is that on the set of the vertices of the graph is the length of the shortest path, for instance. That's also a metric space. Metric spaces are very, very general, like extremely general.
I mean, it is just a space with a distance function. Like the only way you could get more general than is to just remove the distance function, but then you just have a set. So I mean,
you could notice there's an in between. It's called topological spaces, but these ones are like you're not gonna learn topological spaces unless you do pure math.
Isn't topological spaces just the you have distance, but you don't have a value for the distance? Because that's how I understood it. I basically understood it as like you have two things, and then I'm probably wrong on this, but the way I understood is that if you have two things in them, then you don't have a distance function for the distance between them. However, you do have the rules for sets like this, where basically so
you label some subsets as open, and it basically tells you which points are close to which other ones. But since it's so general, you have a lot of really weird stuff that can happen, like really bad spaces that exists. You've got points that are not the same, but they're in the same place. You've got things that are like you've got two different notions of being in one piece, connected and path connected.
Yeah, I
do algebraic topology, and in algebraic topology, like we don't even work with topological spaces. We work with like interesting ones like spheres and manifolds and like nice spaces. but even the people who do homotopy theory, which is something that's much closer to pure topology, they slap like 4 adjectives in front of topological space so it behaves better.
I do.
Like they say compactly generated weak Hausdorff space. I have no idea what it means, but it's supposed to solve all my problems. So I trust.
The best description of topological, the one that explained the best to me was when I was researching it. I came across the topological space just being a space where the concept of closeness is defined, but but you don't or / can't measure it.
Yeah, that's a good intuition, I'd say.
But yeah, no topological. No. We're not getting there today. No, this is Hilbert spaces. We're going with the simple-ish.
Yeah, Hilbert spaces are the nice ones, and like you're never going to learn pure topology unless you're a math major, I think. It would surprise. I mean, no, like don't get me wrong. If you do like very mathematical physics, you're going to know pure topology because
the thing is,
like nearly everything in math relies on pure topology. So if you actually need to know the nitty-gritty details, you need to know what topological space is and how to do a lot of stuff with it.
Reflex, the thing is, like a couple minutes ago, I uploaded the video with Flame, and in order to be on track in like 6 or 7 months, that would mean that I will probably make a video with you, and then so you know, and then I might just get hit with the blast. I might be in the blast radius of topological spaces. That was a joke, by the way. Is that I don't have a video scheduled with you for 7 months. Don't worry. Unless you want to, I don't know.
How far does your schedule go, actually?
I have 40 videos planned right now. Unfinished, of course. I'm not counting the finished ones.
Dang.
If I only wanted to make the videos I have planned, I have like a year and a half, maybe 2 years solid in front of me. But hey, that's what procrastination is for making space for more videos.
Right.
So
today we're doing Hilbert spaces.
So far,
very nice.
okay. So far we've got the metric space. Now
so
complete this next.
So when you have an inner product, you get the metric space, and the Hilbert space is just that you ask for this specific metric space to be complete. That's all.
Yeah, I'm with you so far. That is read up on it.
All right, so these are the definitions. So Hilbert is equal to inner product plus complete. I'm not going to go into completeness because it's not linear algebra and you've already looked it up and I don't think you have any problems with it.
Yeah, no, I actually surprisingly clear, I do have to say.
It's
no
actually do basically.
You cow basic again.
But all the sequences that look like they should converge do.
Yeah,
that's basically what it is. It's the reason why we care about it is that in a lot of theorems that analysis people really like, you need completeness at some point to make them work.
Makes sense.
So yeah. Do I have an example in mind right now? I know there's like a fixed point theorem, but that's maybe not the most like cool application of it, so I'm not going to go into that. Anyways, the whole you can multiply vectors thing and the whole bra and ket notation and stuff.
Yes.
That's the part that irks me a little bit more. So I'm going to actually I'm sorry lines, but I'm gonna remove you. I'm just gonna like take all that we've said and shrink it somewhere so we don't have to think about it anymore. Right. And that goes here. All right. So, what Timon wrote was something like this. I'm going to write them A1, AN, Actually, there's no. I don't know why I put commas there. There's no commas. It's a matrix. En. And you've got a column vector. Sorry. X1 dot xn. And what Timon does is that he multiplies them like so. And the question that you asked is that multiplying vectors? And the answer is no. Why? First, like, do you agree that if you just trust that these are matrices and you do like just the usual matrix multiplication, like this equation works?
Yeah, that makes sense.
All right. Now I'm going to explain why it's actually like it is matrix multiplication. There's nothing weird going on here. The real interesting part is that you can think of vectors as matrices. So kets, they're actually matrices. They're column. It's what Timon says. Their vectors are columns matrices, and covectors are line matrices. But maybe we should like say what covector is. So this is where the linear maps thing is going to be important. Why am I saying this? Wait, did I cut off again?
No. So far, I
No,
can
right.
hear you.
Right. So, like a couple of eons ago, so before yesterday, I told you that a matrix is actually just a function that is linear.
Yeah.
Yeah, that's going to be very important here because now the thing that like
Flashback to top of the board reference.
Yeah. Exactly. So like the thing is that a vector, we represent it as a line matrix, column matrix. Sorry.
Mhm.
Does that mean that a vector is a linear map? The answer is no, but actually yes.
The most mathematics answer. Okay.
What do I mean? When I say that the answer is no, but actually yes, what I mean is that a vector is not a function. Like a vector is a thing in a set. A function is something that takes in inputs and spits out outputs. They're not the same mathematical objects. But a vector corresponds uniquely to a certain kind of linear map.
So hold on. So is what happens here? Wait, are you here? Or you gone? Oh. Uh-oh. Uh-oh.
Oh, yeah.
Okay.
I hear you.
All right.
All right, I'm just reconnecting to the blackboard. All right, so where was I cut off?
You were cut off. Basically, a vector corresponds to a linear math. So, and then you said the word I right now can't remember. The word that I believe means they're like. Fuck.
I'm gonna explain what I mean, but basically, you can identify vectors with certain kinds of linear maps, but not, and you can pretend they're the same thing.
I was about to actually ask a question if what's happening is that you just have like the two separate objects where one of them is where you have just a vector and the other one is a matrix, and then normally you would like have some kind of operation to switch between them, but physicists just don't bother with switching between them, so they just like mash them together like this, and right here are Bra-kets.
I mean, the thing is that you can actually do math to like make this perfectly valid and normal.
When you say you can, do you mean like, is it how it's done, or like is this how mathematicians would do it?
I mean, like when we represent a vector by a matrix, that's what we're doing, like in a way. No, do I actually like do enough? Like, do we write Bra-kets? No, we don't. I mean, usually like the way to pass from a cat to a bra in math, that's something that we do. So if EI is a vector, you can like consider its dual, like that's the cat, and you can the bra we usually we rate it like this. But like, do we spend like so much time doing this that we actually like think deeply about it? Not really. It can be useful in some cases, like if you know what the trace of a matrix is, it's the sum of the things on the diagonal.
Roughly.
Yeah, that's just the definition, but it's not that set. And like it has cool properties, yes, but it's kind of weird. Like, why do you sum the things on the diagonal? Wait, why are you doing that? And there's actually an answer, and you can define the trace without any matrices, like just on the level of linear maps. And to do this, you kind of need this whole switching from bras to cats. But like, yeah, basically, I'm saying it's rooted in math, and the math is not that hard, so I can just explain it, and it should make sense.
Mm-hmm.
All right. So, all right. Let's take a vector. Also, like Ash asked me, Reblax, are you going to read live stream chat to answer questions or no? If you can,
No.
if you want, I can. If you want, I can alt tab like regularly.
I can
just to
read them.
check.
Actually,
Yeah,
I am
great.
going to read them. That's
I
the
don't
usual
have
mechanic.
two screens here, so because usually what I do is just I have Stream open and Discord open.
Yeah, it's fine. I
and,
mean, I
nice
can read them. I have
monitors, so yeah.
the
All right,
other
great.
screen.
So let's take a vector. How does matrix multiplication work? Like, how does a matrix represent a linear map? Well, we know that a matrix, when you like stick a vector to its right, it gives you another vector. Right?
Mm-hmm.
Provided that they're the correct dimensions. So like this length is this length.
Right.
Right. So that means that a vector, if we represent it by this matrix, it should be a function that takes in a 1-by-1 matrix. Or at least like it, not really not only a 1-by-1 matrix, but basically like if we want to do the simple thing, which is the thing I want to get to, it should take like just a 1-by-1 matrix. Like this, what I'm saying is this is a legit matrix product that you can do.
It makes sense, yes. But I mean, it shouldn't, but it actually does make sense.
Which, like, obviously, because a 1-by-1 matrix is just a scalar.
Yeah.
And, like, you just scale the vector. Wow, Reblax, so cool. You should get a Fields medal for that. I know. I'm handsome and very smart and stuff. But let me go even further. So what are the scalars here? Well, we said that scalars were real numbers. So that means that our function, it takes in a real number, and it spits out, well, a vector. I'm gonna write the theorem. It's not really a theorem. It would probably like be a proposition at best. But I don't give a shit. It's my lecture. I do what I want. All right. So V is the same as, I'm going to explain what the same means in a bit, as linear maps, which I'm going to write with this fancy L, from R to V. All right, so like so far I've taken a vector, which is just a column. As a matrix, it's a column. And I've said that it's a linear map that takes in numbers and spits out vectors.
Right.
Everything up to that point should be like at least okay.
Yes.
Yeah. So yeah. And actually, like if I write this just in terms of like actual vectors and not matrices, basically the function, basically like I take some vector x in V. I'm going to write this down. I take some x in V. Well, I'm just going to write x, and since it's below V, we know it's a vector. And it corresponds to the map that takes in a scalar lambda and spits out lambda x.
Mm-hmm.
All right, that makes sense. Cool. Now we need to go the other way around. Like if we have any linear map, can we find such a vector? And the answer is yes, because everything works out really well. It's linear algebra and stuff. So how do we do this? Well, we take F that goes from R to V. It's a linear map. And like we want to find our vector X such that F is this map. You might notice that if we take lambda equals 1, well, we just get X.
Mm-hmm.
So like that tells us that we should probably like put F of 1 here.
Mm-hmm.
And that works. Basically, it just works like this. If you have a vector, it induces a linear map from the real numbers to the vector space by just scaling the vector. And the other way around, if you have a linear map from scalars to your vector space, well, you can assign to it a vector that is just f of 1. And like, why is this a really good way to pair the thing? Why is this a really good way to pair things up? Well, it's bijection. It's a bijection. What does that mean? It's a fancy math word. It's a fancy math word to say that both operations are inverses of each other. Why? Because if I have a vector x, well, then I do.
No, no.
And if I take lambda equals 1, I just end up with x.
I think I get it.
Yeah, basically I'm doing like this,
Mm-hmm.
then this, then this. And I notice I end up in the same spot.
So
The other way, yeah.
no, do carry on.
Right. The other way around, I just like take a linear map. And I'm sending it to f of 1. And then f of 1 is a vector. So I'm sending it to the map given by lambda goes to lambda f of 1. And like that's the very important part. I said f is linear. And here we're scaling
Linear by lambda.
Yeah, exactly. So this map is actually exactly this one. Because like f is linear, so I can just like take the lambda and put it inside the brackets.
Oh.
But like the map that is in lambda and spits out f of lambda, well that's just f, like that's the definition of f. So in both cases, when I do like my nifty process and I return to where I started, I haven't changed anything. So like that's what's called a bijection. A one vector corresponds to precisely one linear map, one and only one. So you can safely pretend that a vector is a linear map and everything works out great.
That makes sense.
There's a little bit more, like, it's not just a bijection, it's even an isomorphism of stuff. I'm not going to go into that. But basically, it's even better than that. It works even better, in fact.
Wait, so can you treat all vectors as matrices always? Like, can you treat them?
Yep. Well, matrices are for stuff in finite dimensions. So.
Oh.
you need to have a finite number of dimensions.
Okay,
I mean,
I'll
you
be
could pretend. Yeah, you could pretend that you have infinite matrices, and like I've definitely heard someone refer to the Fourier transform as as infinite dimensional diagonalization of a matrix, and that person was a physicist. So yeah, I mean, yeah,
I'll
like
be brutally
even
honest with
like
you.
even in math, there was like at least one time, it happened a couple times actually, where we had an infinite dimensional vector space, and we had an inner product of two things that normally would make it look like a matrix coefficient, but here we were in an infinite number of dimensions, and we didn't care. We still called it matrix coefficient. Like, yeah, the we just don't write out the matrices because sheets of papers and chalkboards tend to have a finite area. It, it works, but it works exactly the same.
I gotta be brutally honest with you. I still have no idea how infiniteness changes stuff.
I mean, I'd say the main difference between finite dimensional vector spaces and infinite dimensional vector spaces is that when you have a finite number of dimensions, doing limits and stuff is way easier.
Okay,
There's a theorem. There's like a theorem. It would be like it wouldn't be a long. It would take like what kind of a long time to explain it. But basically, when you pass to
Okay.
infinite dimensions, your linear algebra just becomes functional analysis because you need like topology. You need to bring in topology to actually do stuff. But in finite dimensions, you don't need that. There's a cool theorem that like saves you from doing that. So it's pure algebra. Everything is like it's easier.
I do
I mean,
have
that's like yeah.
a bit of a question, because if I learned one thing, like the one overarching theme of every single one of your explanations is that like everything can be done if it's interesting enough in math, and so in that kind of spirit, I have a question: what is like the motivation behind this being different than this? I know they are different. It's just that
Yeah.
what will be the motivation
Oh,
between?
I was going to.
I think you cut out again, Roblox. Hi, the stump. I'm just there. Maybe I'm the one who's cutting out. Dead alone.
Oh no. All right. I'm back. Oh, hi, Stamp. All right. Am I back?
Yes, you are back.
Yeah, we are so back. Anyways, you're right. You're kind of right. Like, it's quite subtle because they're the same in a way. In fact, in a lot of ways, and there's too many of them, and we don't really know how to pick one. But when you have an inner product, you know, like there's one good way to pick one, and that's why physicists are allowed to identify bras and cats. And like I was going to explain that after.
Oh, okay then.
It's a very very interesting question basically. And I'm going to like do that now because I talked about vectors and that's cool. We like vectors. Vectors are nice. But what about covectors? Well, we're going to do like the same technique here. Like we said, we want to find out like what actually a column matrix is, and we just looked at the size of its inputs to determine what it does. And we figured out it could take in real numbers and spit out vectors.
Right.
Right. We're going to do the same for a covector. A covector, it takes in, I mean, it's the equation I wrote here. It takes in a vector and it spits out, well, a number.
Mm-hmm.
So here, a matrix that's a line, it corresponds to a linear map from the vector space to R.
Right.
right? And so what you're
Opposite.
doing,
Okay.
yeah.
No, I just.
So what it's not the opposite. We call it the a dual, actually. In fact, this space is so important. We usually rate it V dual, V star, or V asterisk.
I am sensing a pattern with the star, but do carry on.
In fact, like yeah, basically when you have the star is for when you do linear algebra. And wait, am I disconnecting again? No, I'm
No,
fine.
you're
Great.
sure.
When you do linear algebra or analysis, when you do vector spaces, basically you use an asterisk. When you do like pure algebra, at some point you start not using an asterisk, and instead, if you have something that looks like a vector space but isn't really, you write it like this with a V. I had that in my commutative algebra exam, actually. Anyways, it's more general. I can really talk if you'll ask questions if I have any. I'm moving stuff in my house right now. All right, that's fine, Stamp. Make it is supposed to read the chat and
Yeah, I didn't read
see.
it out loud because the stump was in here with a voice chat and you were explaining.
Anyways. So what we're doing when we do a matrix multiplication is that we have two functions, two linear maps, and we're doing one after the other. That's the stuff I explained like on top of the board. Stuff that you said made sense to you now, like this diagram. That's the very important thing. So when I write out this matrix multiplication, well, I have a vector, and the vector is just a function from R to V. And then I have
it
vector.
clicked.
Yeah, it goes to R.
Oh my god! And if you do it the other way around, then you like okay.
Yeah,
So this would be basically like VW.
You can do it the other way around. Yeah, you can also do it the other way around.
And then you end up with a V. But wait, if you do it the other way around, wouldn't that be equivalent to kind of like a ket bra like this?
Yeah.
And then you
That's
get
how
back
physicists would rate it, I guess.
something in the vector space?
No, because when you multiply two things, you get a function like this, so you get a square matrix.
Oh, okay.
But actually, like doing this, well, it works and it's important, but basically it gives you functions from V to V, so square matrices, but it doesn't give you all square matrices. It gives you only a very specific type of square matrices that are like, it's matrices that have rank 1, so it's very not invertible matrices, basically.
I have a question. Doesn't a ket bra indicate cross multiplication or cross whatever?
Cross product?
Yes, thank you.
Ket bra. I'm not too familiar with Bra-ket notation because I've never actually done quantum physics.
It's apparently the opposite. I mean, not the opposite.
Could it ket into a bra at some point, which is the next thing I'm going to explain.
Totally cut out again, but
all right, great. But I'm back. So yeah, the thing with Bra-ket notation is that you have to like turn a ket, so a vector, into a bra, so a covector, and that's where the inner product is very important. So wait, hold on. Does a ket bra give you the cross product? Like, it feels kind of weird to me because like the cross product is supposed to give you, well, first the cross product is like something that exists in like R3, but let's pretend we are in R3. So we've got this, and the cross product is supposed to give you a bivector, right? Not actually a vector, but bivector. But like it's the no, I don't think it works out. Like the dimensions don't seem to. I don't think the dimension checks out.
I just think I read that somewhere.
Well, I mean, it could be physicists abusing notation, or maybe I'm just like dumb, and if you do the right isomorphisms, it works out great. But I'm not gonna say anymore because I don't want to say something false.
Yeah. Okay. Thank you.
Right, no problem. All right, I'm gonna move that here. No. Make it asked the very, very important question. Hold on. Isn't a covector and a vector kind of the same?
Yeah, what's the
And
reason
answer
for
is,
treating it differently?
well, I mean, like, the first reason is that one is a function from R to V and the other one goes the other way around.
Yeah, okay, that makes
So
sense.
like they're not the same mathematical object.
Mhm.
It's kind of like if you have a function, you can curify it, and it doesn't really change the underlying process, but they're not really the same, are they?
Yeah.
If you ever don't like, if the people who have done some programming in the chat will probably have the reference. Anyways, yeah, lambda 2 of v isn't the same as v tensor v. Yeah, that's the thing. Anyways, yeah. So x1 to xn. You could say, what if I take this vector and I write out this covector? That's a reasonable question to ask.
Mhm.
Like, in one case, there's n numbers. In the other case, there's also n numbers. They're kind of the same, and you're right about that. There's a notion of being the same for vector spaces. That's called isomorphism of vector spaces, because we mathematicians are very creative people. That's bad. I shouldn't like self-deprecate like this. Mathematicians are try to not be too creative when it comes to naming things, except Grothendieck. Grothendieck and a few other people.
I would say lack of creativity is really good when it comes to naming, because then you don't need to learn all the names. You can just figure out what they mean. But at the same time, Grothendieck gets a pass because I mean, I feel like he ended.
I mean,
Yeah, but then you end up with situations like spin, or like up down strange, top bottom.
No, spin came
charm.
from trying to be too creative. Actually, same with top bottom. That came
I
from.
thought it was because
No,
I thought it was because we thought that they were spinning.
No, they behave as if that's actually came from, like, actually angular momentum quantum number, for example, is surprisingly accurate because you just have angular momentum without spinning. Hence the confusing part. How can you have angular momentum without something actually spinning? But yeah.
Oh, that's the part that made sense for me.
no, actually, top and bottom come from physicists being gay.
Little known
As
fact,
we
actually.
all know.
Yeah.
So good physicists.
Yeah. No, anyways, no, I mean, in math, like, sometimes the name of terms is a little bit far-fetched. Like, you've got, well, vector space makes sense because it's a space of vectors. It's stuff that behaves like vectors. But if you do other algebraic structures, you have groups and rings and fields. And like, I have no idea why fields are called fields in English.
Yeah,
In French and German,
yeah.
yeah.
It's awful.
In
Yeah,
French
that
and
part
German, they're
confuses
called
me some.
core. So they're called core, which translates to body. But actually, it's because of army corps, because a field has a lot of structure. So the people who came up with the term were like, "Oh, it's like an army, it has a lot of structure." I think that's the story behind it. You've also got some agricultural You've also got like some agricultural terminology going on in like what the stuff Grothendieck was doing.
Very.
Beef and like
I
gerb or whatever.
I do have to say, very French of you. That is just I can't explain it, can't put into words, but that is just very French to have
Oh no, but the
fields
funny
be
thing is
cores
that
too.
actually, like, the funny thing is that there's something called sheaves, which are very important in geometry. Well, modern geometry. and like it wasn't Grothendieck who invented them. It was another French guy. And they're not even called, they're called like beams in French. So no agriculture going on there.
Leo actually just said, I thought they were called rings/fields because of Hilbert, and it's just bigger and bigger things. Group smaller than a ring, like a boxing ring, smaller than a field corn.
Well, I don't know about rings, but feels like it's because, well, fields in English, maybe they're called fields because of this. I was speaking like of the French and German words for it, which is not the same. It's a corpse, as in like an army corpse. If that makes sense in English. But yeah, sometimes there are reasons.
Something.
Today, my internship mentor ranted to me about operads for an hour, and the origin of the term operad is like just some algebraic topology dude pondering for a week how we should call.
Damn it, he called the punchline. Piss. Energy from algebraic geometry, notion of size, kind of reverse, fields points.
Fields, points, ring schemes, yes.
You cut out
Yeah,
right before you were
true.
about to say the punchline. To the story.
Well, basically, like the guy who invented Peter May, the guy who invented operads, pondered how we should call them for a week, and then he came up with operad, and now we all call them operads, and they have nothing to do with opera. It's because they're like they look like monads and they encode operations or whatever. Yeah, and I mean, like it's something that has a lot of operations, so the name makes sense. Anyways,
I mean,
so what's wrong with taking a vector and like just putting it on its side to get a covector? Well, basically you've got two spaces. You've got L of RV, which is just vectors, as I already said, and you're trying to make it look like
LVR.
LVR, the dual, exactly. And in fact, that works. As vector spaces, they're the same. Because vector spaces have a really weak notion of being the same. Two vector spaces are the same if and only if they have the same dimension. And like here you have n numbers in one case, and you also have n numbers in the other, so they're the same. Like doing this works in a sense. The problem is that actually, what if you were a little bit funnier and you did this?
Backwards.
In
I
fact,
see.
that also works. It also gives you an isomorphism of vector spaces.
Oh, but this.
What I'm getting.
Oh yeah, so you have two basically equally justifiable ways to turn a vector into a covector. Wait, would this
not
still be
just
covector?
two. Not just two.
Oh, because you can
whole
flip
lot
them.
more.
Okay, that makes sense.
Oh no! You can even do worse than that. You can put a 2 here, like for shits and giggles.
Okay,
and
I see.
that also works.
Uncountably, infinitely many ways to just.
Exactly.
Okay.
You have uncountably infinitely many ways, and you need some way to like. You need to pick a preferred one, and you need to have a good reason to do so. That's because like here we're doing matrices, so we kind of want to like just flip the matrix on its side. But the way we think of vectors as matrices kind of depends on the choice of a basis for the vector space. So technically, there's some choices going on there, and there's no like one true way to make them. And that's where the inner product comes into play. The inner product allows you to make a canonical choice. How does it do that? Well, we're going to talk about I'm going to like do something that may make the functional analysts angry and call that the Rees representation theorem, even though it's a much weaker version of the actual core theorem. But whatever, I do what I want. It's my lecture. Right. Now, now we assume that we have an inner product on V. All right, one inner product. We know it. It's there, right? Well, let's pick a vector in V, and let's look at this map. This map is linear. Why? Because it's an inner product, and like the first vector I put into it, it never moves. So because it's bilinear, but I fixed the first vector, it's linear.
Makes sense.
That's the thing here I wrote. So it's a linear map, so that's nice. That's a sign we're doing something correctly. And where does it go and where does it end?
So for now, I have no idea what's going on in the lecture. Well, that's even worse because Reblax's internet keeps cutting out, and I'm just scared he's gonna come back with just like 3 whiteboards full of text.
And anyways, that's why if we have a non-trivial zero of the Riemann zeta function, its real part is 1 over 2.
No.
Any questions?
You just cut out and you come back. Yeah, exactly. And so these are basic. And so here are the list of 12 unproven theorems I just proven. And then damn it, my whiteboard lagged out. Everything got wiped.
Yeah, I cut out again. I think. Anyways, yeah, we're back. Right. So, what's your question? Make it.
I don't have one. So far I'm with you with this.
All right. So we've taken a vector and we've found a covector. I keep saying covector because of lemon actually, but no, the math word we usually use for this would be linear form.
That's way less cool. I prefer lemons.
You're less cool.
Whoa, calm down. We're all friends here. Let's calm down, okay?
This is like lecture 1 of the missing linear algebra for pure math 3-week course. Yeah.
Except this isn't really lecture 1 at this point. I feel like we're...
No, it's not lecture 1, but it's for missing linear algebra because I've heard that people in the US, when they go to grad school, like from undergrad to graduate school, sometimes there's math they're supposed to know, but they actually don't. Like, well, probably like some, I mean, me too, like, technically never did, I never formally did complex inner product spaces in a linear algebra course, but like, I've done real ones, so I can just wing it, it's fine. And it's not really winging it, it's just a matter of looking up definitions, noticing that, all right, this works like this works like this, fine, great. It's okay. All right. So we've taken a vector and we've gotten a covector from that using the inner product. What I claim is that this is actually a very good way of doing stuff. What do we mean? So basically, I've taken a vector from V and I've sent it to an element of the dual, which is inner product with X. And the same as before, if I have some phi that goes from R to V, from V to R, sorry. So a linear form or a covector, depending on your religious beliefs. You can actually find a vector here such that phi is the inner product with that vector. So like all linear maps, all linear forms arise this way. And the way to prove this is that you could like do it explicitly using a basis, or you could do the GigaChad mathematician move of saying that the map is injective and you have equality of dimensions, so it's an isomorphism. I'm not going to go into the details, but basically you have a very quick way of doing this.
I just want to say that I already understand what I was confused about last time. And what I really like here is that this is kind of like the graph, the normal distribution of people graph, where you have vectors are just matrices, vectors aren't
Right,
matrices, vectors are just matrices. Or other vectors are just linear maps.
That's actually like something that's very, very, very interesting. Like it's a property of R basically. This is just this. In much the same way, if you have a Z and a group G, you have something that looks like this. And hom is the functions that respect the group structure, the group homomorphisms. Like it's a very similar thing. But yeah,
Like, stop
like,
bringing everything back
there's
to
something
groups.
there's something very interesting going on here basically, and I'm not going to go deep into it. But yeah,
Like, stop bringing back the groups, please, I beg you.
the work is hidden in showing that V star has the same dimension. You need a billion group there. Do I? No, because right, yeah. For this to be actually, yeah, to have an internal home, I need an abelian group. But just to have like a set theoretic bijection, I don't, because I can just like define my morphism like this. And that corresponds to G. But yeah, you're right. It's not exactly the same. It's a little bit weaker because it's an internal. It's because we don't have internal homes. So yeah. Yeah, because like I may have already told this on stream, but abelian groups are just vector spaces over Z. But I didn't tell you this. This is a secret. You're not. You don't discover that until your third year. Oh, so yeah, the bijections are natural. That's like that's the important part. Anyways, my point is that in general, V and V star are the same vector space, but you need like to pick one way of them being the same. And usually you don't have one preferred way to do so. And in fact, you can like show that there is no one good way to do so. For category theory reasons, there's no natural way to do so, to do so. You need to make a choice at some point. But if you have an inner product, then we have one very good way of saying these two vector spaces are the same. And so that's what the physicists are doing basically. Because if you have a vector psi.
So basically, the reason why you can turn. Okay, so wait, the reason why you can pick a cov. I'm gonna keep calling covector. Sorry, it's catchy. The reason why you can pick a covector V to a vector V is because you're walking in the Hilbert space.
Just an inner product space works.
Yeah, but I mean, in quantum mechanics specifically.
I'm because I did everything in like finite dimensions, but maybe if you do it in infinite dimensions, you maybe need.
Yeah, but in quantum mechanics, they deal with finite dimensional
Hilbert space. It works in the Hilbert space.
I totally understand this. Toby, don't worry. The next 2 videos on the channel will be about this, so.
Hi, Ta. Welcome to the math lecture.
Hi, Ta.
So yeah, that's what the physicists are doing when they write a bra using a vector. They're actually identifying the vector using the inner product, and like that's the very important thing. Like I think you know that when you write psi ket psi, you just get the norm of psi squared.
This makes sense. I mean, I do have to say, this is wild because, like, I knew this for months, but it's mad how much background mathematics most textbooks skip over.
And like, if you look at the specific isomorphism I've written, like to a vector x, you associate the linear form that's the inner product with x. Well, what if you then evaluate this covector on x? Well, you get exactly x inner product x, so precisely the norm of x squared. So this shows I've done things correctly. I mean, like it's coherent with what the physicists say.
He said helium had 8 valence electrons the other day. People make... You can make mistakes, you know. 2, 8... Okay, to be fair, it is a weird aberration from the octet rule, right? Is this another view inside the mind of a mathematician? Or mathematician, I don't know how to read that. Yeah, this is basically like... This is Reblox.
These days I don't even like do actual math. I just write a commutative diagram after commutative diagram after commutative diagram, and none of them work and do what I want, and I'm very sad.
Bra-ket also lets you be agnostic about which V and which corrective V, because that is also an arbitrary choice. You also stack
That's
writing
a very
one
good remark.
which can equivalent choice.
Sounds like algebraic topologist. Yeah.
Wait, so
I'm not like pure algebraic topologist, but yeah. I'm not really anything for the moment. I'm just a master's student, so yeah.
my phone refuses to let me type mathematician. That's a good phone, though. I feel proud of myself that I understood this. By the way, it's the little wins in life that matter. Because okay, so basically the takeaway here is that you can treat vectors as linear maps and linear maps as vectors. And also, if you have the inner product, then you also have the best way to switch from a vector to a covector.
It's not really the best way, but it's a specific way that works good with the inner product structure.
The best in quotes, of course.
Yeah, it's
like a unique.
It's a designated way to do so, basically.
Okay.
It's like if you've ever heard of the matrix transpose, it's related. It's also related. Like you've got an interpretation of the matrix transpose that works every day. It's just switching the inputs and the outputs, basically. But if you have an inner product, you don't need to do that. You can also like talk about what's called adjoints. I think is that what they're called in English? But yeah, basically inner product works great.
Yeah. Life is context. The inner product gives you the best way in that context. Yeah, I already learned that the hard way when I got yelled at by Reblox last time.
Yes, they're called adjoints. Great.
Actually, it's not that you can't multiply vectors. It's just that in this definition of linear algebra and the base axioms, there is no proper way to multiply vectors, and therefore you can actually multiply vectors if you create a definition for the multiplication. Mathematicians taking all the fun out of fun things.
We've got a lot of interesting math to do with that. For instance, like semi-recently, using a little bit of algebraic topology, you can show that if you have a way to multiply vectors, to multiply n-dimensional vectors, such that the product of two things is 0 if and only if one of the two things is 0, at least, then the dimension is necessarily...
No! The worst possible... You cut out the worst possible time.
Oh no. do they do?
Well, when you said basically is, and that's precisely what you cut.
Okay. But if you had a way to multiply vectors such that it's integral, so that means that you have the, that rule when you have two numbers and they multiply to 0, it means that at least one of them is 0.
Yeah.
If that works, and you're in n dimensions, and you're over R, well, actually, that means that the dimension must be a power of 2. And you can prove that using topology. And in fact, you can, using more topology that I know, you can prove that the dimension must be 1, 2, 4, or 8. And these are the only possible cases, and they're given by R,
That's
T, the
wild.
quaternions, and the octonions.
That's wild.
And that's like very cool, because it's an application of, it's an algebraic question. You're asking when can you multiply vectors with another hypothesis, and the answer is given by topology, algebraic topology. And I'm not going to try and explain that right now because
Oh, please don't. Okay.
because it's 1:30 a.m. I'm probably going to mess up and other stuff. This feels like something you might need to do a spectral sequence for. You don't need spectral sequences, actually. You just need to know about characteristic classes. And like the cohomology and like calculating the Stiefel-Whitney classes of the tangent bundle to real projective space, which and you can avoid doing spectral sequences for that.
Is that what it sounds like when I'm talking with Flame on stream? Oh. Okay, good to know.
Yeah, it's Leo, if that interests you, it's done in characteristic classes by Milnor-Stashev, like towards the beginning of the book. So you can go look in that if you want to know the reasoning behind that. I mean, you don't need spectral sequences, but you do need to like construct Stiefel-Whitney classes, which is non-trivial. I'm gonna write it in chat. In fact, I can probably like find the page. Do I have it open? Yes, I have it open. I always have it open. Once it's done. The specific application to real division algebras is on. Where is it? Immersions nobody. Yeah, 4.7. 4.7 on page 48. I've been wanting to relearn some algebraic topology for economics, game theory stuff of all things. Yeah, I'm not going to get too based on stream, but I have opinions on mathematical economics, and at some point I went to a seminar given by mathematical economists to try and challenge my opinions, and they just came back stronger.
I'm curious now, what are the opinions?
I'm not kidding, but like at the start of the talk, the guy straight up tells us, it gives us a quote by one of his colleagues, who's also a mathematical economist. The quote is straight up, game theory explains the real world like a fable explains the real world.
Oh, is it just... Oh my goodness. Is economics considered mathematics?
No, economics is not mathematics. I mean, it's applied mathematics, if anything. It's applied mathematics.
But like, it's applied mathematics in the sense that chemistry is applied mathematics.
Well, it's more like the thing with economics is that you can make simulations and stuff, but you can't really do experiments. Like you don't have people putting countries in a test tube to see if the growth is going to grow up by 3% next year. Even though I'm sure they would really like to do that, but
I mean, no, you can't choose your experiments, but you can do experiments. You just check the real world data. That's your experiment. The only difference is that you can't affect your experiment, like you can't control your experiment much. But other than that, you can make an experiment.
Right, so I was cut off for a brief time, so I didn't hear like the probably last 3 sentences you said, Bra-ket.
Oh, what I said is that you do have experiments, it's just you can't control them because you can still have access to data, and the data is kind of like
that's true. That's true.
And in that sense, I really don't see how calling
Real
economics
accuracy. I mean, it
applied
depends on who's
mathematics.
doing what. You have scarce data. I mean, yeah, I agree that like it's. I mean, I'm not like against the whole fundamental premise of economics, like obviously understanding how money works in society centered around money and stuff is a good idea. But like I mean, I guess the problem that most of us have with economics is that sometimes it can be very shaky because of the scarce data, and you have people pretending it can explain a lot of stuff and making policy changes based on that supposed on the supposed models that are backed up by mathematics and stuff.
Economics game feature of anything where use the main spaces.
Oh, if you're like referring to stuff like you can what did I yeah in a French algebraic topology book I read about social choices. Like if you're trying to make a voting system with a continuous space of outcomes, you may run into problems because of the topology of the space of outcomes.
The thing I have with economics is that I believe that the only value economics has is the data itself, which is basically if someone says, if someone talks about economy, then the best way to shut them up is just to give them the data, because either the data agrees with them and then you can just shut them up because there is nothing more they need to say, or the data disagrees with them, which is a very satisfying way to shut a person up. And I don't really like the creation of too many theories behind the data, because I mean it's really easy to fit something into the, like if you have a certain amount of points on a function, you can define quite a lot of functions based on those points. And then
Yeah, that specific voting proof I think has a ridiculous model Mayo. Yeah, it's ridiculous because in like nearly every instance of where I can think voting happens, you absolutely do not have a continuous space of outcomes. Though I will say the proof is quite nice, and like I think it's interesting from a pure math perspective, but as a model, absolutely not.
often with the flag of mathematically proven when most of the content is in the model assumptions. That seems like quite a big difference.
Yeah, that's like I remember because like at the talk I mentioned like the speaker like lost quite a bit of time because he asked the audience to model something, an interaction between two humans, and all of the answers everyone gave were too altruistic. And like I figured out what he wanted us to say like before he said it, like right before he said it after like 16 failed attempts. No, I'm going too far. Like 6 failed attempts by the other people in the audience. But like yeah, there's a lot of assumptions made in every model.
I mean, yeah, mathematically proven is the platinum standard of scientific proof. It's like doesn't really get much higher than that. I wouldn't exactly place economics there. Mathematically proven would be like the theory of everything level, where, for example, if you could have some kind of emergence from pure randomness, then physicists would probably try their hardest to make a theory of everything based on that, because that would be the simplest basically description of the universe you could have. Just assume that everything beyond quantum is pure noise, pure randomness, and assume that quantum is just the emergent properties of that, just like classical mechanics is emergent properties of quantum mechanics. So in that case, you could have a mathematical proof of the theory of everything, which would be the Platinum standard. We, however, are on the opposite side with fragmented theories and, well, kind of shaky evidence with a particle that is no one even has an idea of how to measure. Don't tell Remco I said that. No, I'm just kidding. You can tell Remco I said that. Remco knows very well my opinions on the graviton. I think we should just scan the Babel archives for the answer.
Oh yeah, Nash equilibria. You can prove the existence of this using the same thing that's used to prove the Brewer fixed point theorem. Can't you? No, wait. Did you use the Brewer fixed point theorem to prove that Nash equilibria exists? I don't know. I know there's like. I know I cannot. I know I can pretend like my research has real applications to beg for funding. Is my point, and that's good enough for me. In fact, I should stop like acting like pure math is useless, because it's really not. Like, people are analyzing data sets using algebraic topology right now. And even algebraic geometry and number theory, people have invented cryptography based on elliptic curves. So, yeah.
It's just, you need to just give it some time to simmer, to then move up. You need to give it enough time, basically, for that one weird physicist to pick it up. You know, that one guy who's like technically into physics, but actually dabbles in math an awful lot. You need to wait for that guy to pick it up, and then he's gonna like spread it to their physics friends, and then they're gonna like spread it to the chemists, and then you know, it goes, one random YouTuber makes a video about it, and you know, it goes mainstream. That's actually what happened to addition, yeah, and it wasn't. Multiplication. Yes, no one knew what multiplication was until Markiplier made a video about it, and that's where we get the name multiplication. It's because Markiplier made multiple videos, and multi plus Markiplier, and then multiplier was born. History is interesting. It's really curious.
Well, has there been a success in persistent homology? I don't know. I don't know either, but persistent homology is definitely closer to having applications than just people musing about H cobordisms or I don't know what.
You mean a mathematician meets a physicist?
Anyways, I think I'm going to go because I need to like sleep and
it's fine.
and go learn about spectral sequences tomorrow because
I should
I
go
need
to sleep
those.
as well. Oh, the video is performing like absolute shite. Well, I'm glad to know. It's fine. It's been a while since I cried myself to sleep anyway. I should, yeah. It's good to have a reason. Yes, Lagrange Markipliers. I have no idea how to pronounce that name, by the way. I always just butcher my way. Yeah, no, I'm not. Yeah, no, relax. No.
The hard. Alright, la is la. Je is je. The problem is the en, which is a weird as vowel we made up. I mean, actually, maybe it exists in English. I think the only vowel we have that doesn't exist in English is u. But you know, the nasal vowels aren't too common. You would hate my American pronunciation. Considering how much I butcher the name of every non-French mathematician, I think I would be fine. Wait, actually, like, do you know, like, I'm going to send the name of a mathematician in chat, of a computer scientist in chat, and without looking it up, can you tell me, make it, how you would pronounce that?
Is that the one? Oh wait, is that the one you've said it before, and I don't fucking remember. But I don't fucking remember. I remember it was
clean.
really.
Yeah, exactly. It's actually not clean. It's fucking cleany. Look it up on Wikipedia. Stephen Klein. It's cleany.
It's clear.
It's-
I
Fucking cleany.
I remember because my guess was the same as Taz, was either Klein or Clean. And then you just put up with the Cleany.
Anyone I meet.
And yeah, and weren't there the thing where you were, was it giving like a lecture? Or I don't remember what, but you were giving it, you just mispronounced it the entire time. Because you had no idea it was, who would have just, it,
I guess it's or anything, so
cleaning my ass, yeah. I don't know, I still pronounce it the broccoli wavelength, so I think.
what do you-
And he's gone again. No, Reblox! No! Come back! Avocado's number.
Is
That's
did I phase out before
yes.
before I said uh yeah, so I pronounce it nutter in French. So nutter in English, that's like it's probably not correct. Nether, no.
Nothing
Nutter,
better.
butter, yeah, something
Not
like
a,
that.
that's not you. No, you mathematicians need to get better names. Honestly, I mean, there should be a
It's a genre
rule.
where there were actually two of them. Like there were Max Nutter and his daughter Emmy Nutter.
No, no,
And Nutter wasn't even French. She was German, I think, maybe Austrian. She wasn't French, is my point. And in fact, Max Nutter, like if you go on his Wikipedia page, the first thing that's written is Max Nutter is a German mathematician. He is most well known because he's the father of Emmy Nutter. Your best accomplishment in life is you had kids. They did
That's
better
rough.
math than you.
That's really, really rough.
But also, Emmy Noether is like important because she was like a woman in the time where being a woman mathematician was harder than it is now.
I feel like
she had to teach under Hilbert's name at Göttingen because some people were uncool with a girl doing math.
I think there should be a rule like with popes, where just if you get to a certain level of mathematics, you need to pick a new name. And like instead of that, that sounds like a very mathematician. Yeah, and instead of just like with these weird unpronounceable names, you just pick like John or Paul or something. I know the space.
I'm not gonna dox myself, but I have a compound last name, and one half of it is Polish.
Oh, no. But I feel like that would be good rule. You know, instead of talking about, I don't know, Hilbert got it kind of right, but I mean, you know, like spaces of John the Third, like that sounds so much better.
John homotopy theory, but the homotopy theorists, they have like reasonable names like Frank Adams, or is it Adams? That's not the problem of the name. That's the problem that English is a stupid language with weird vowels. But like Postnikov is probably pronounced Postnikov. Who else did homotopy theory? Quillen. Quillen is pronounced Quillen. Is it like just Adams? Adams.
I think it's Adams. Like I mean, I'm guessing like John Adams,
Adams.
right?
It's Frank Adams actually.
I was comparing pronunciations, but yeah.
Adam, like Adam and Eve. Frank Adams. Yeah, that sounds about right.
My first name is John.
Oh, you like?
No, my father was Mr. Homotopy Theory. Call me John.
I mean, like the guy who invented operas is Peter May. You can't really get much better than that.
I know Peter Might would have been a solid choice. You'll realize that in most countries, like you could apply for a name change. I'm just saying, John Mathematics is right within your reach. Fucking hell! Can you imagine?
I mean, there's a practical reason to like for mathematicians to have names. There's a very good reason. If you struggle with a math concept and it's named after the person who came up with it, you absolutely know who to hate right now. Right? Do you have trouble with Quillen equivalences? You curse Daniel Quillen. It's that easy.
Okay, but imagine, but like, listen. Picture a textbook, right? Or just a book on some topic.
No, in
Okay.
fact, I can pick up a textbook right now. I
No,
have one.
no,
right here.
but picture it and pick some kind of title. It doesn't matter. Topic title doesn't matter. And written by Redblacks. It doesn't have that appeal, okay? Like, nothing against you. It's just like any other book, okay? It doesn't have that kind of appeal. Now imagine the same exact book, except where the credit it says by John Mathematics. Like, I mean, come on. That's like having a signed copy of the Bible.
In fact, like you're right. Like I know of at least one. I mean, I have two examples of mathematicians who published books under alternative names, but the first one is Bourbaki, so it's Bourbaki, so it doesn't really count. But there is another guy, French mathematician, who's called like Jean-Louis Laudet.
Please let his name not be French this time. Changed. Now the one he.
GW. Hold on, what was it?
That's not a good start already. GW is a pretty.
GW Znibiel, which is Leibniz but backwards.
No, that's awful.
Bourbaki is fine. Bourbaki is very fine. I mean, it's the name is fine. The rating is Bourbaki.
Read the book of engineering written by John Airplane and Joseph Wright.
Wow, I can't wait to read that book on stable homotopy theory by John Sphere.
You would go hard though. I mean, like John Sphere would know.
Yeah.
Okay, don't like most last names come from professions?
If mine comes from a profession, I don't want to know what that person did.
No, because okay, most like a Smith, for example, you know, most common was Smith. Is that because mathematicians just don't reproduce? Is that why? They're just.
I mean, I can't argue with that logic because the bloodline ends with me. So
Honestly, I feel like that's how society works. We just the reason why we have mathematicians isn't for all the mathematics stuff. Like mathematics was invented simply to end bloodlines, to stop overpopulation.
yeah, it's a more advanced form of birth control.
Actually, now I think about it, there really isn't any last name like physicist or chemist, so I guess that might be more of a science thing.
But that's because like 100 years ago, well, like 120 years ago, scientist was just a job description.
John Mathematics got tired of not having sex, so he decided that nobody else can have sex.
No, actually, John Mathematics got so tired of not having sex that he invented game theory. Unfortunately, he did forget about game
It
practice.
did not work.
I can't wait to read that easy and painless guide to the spectral sequence in 10 steps by John Homology. And the easier and painless your guide in 10 very cool steps to the spectral sequence in cohomology by Kojan homology.
Codon homology. But do be careful when reading the works of John homology. You don't wanna. You wanna be careful. We want to be careful of his cousin John homophobic. It wasn't mathematician.
I saw this coming from a mile away, but it still made me laugh. Holy fuck, I said mile. Oh no. John Mathematics got so tired of not having sex that he invented sexy prime numbers.
Actually, he didn't really care much for after getting up in the morning, taking care of himself. So he just went like, screw it, Harry Ball theorem. Why as well?
Fuck, Leo is right. It's John Serre. Like Serre. His real name is Jean Pierre, but Jean is French for John.
Actually, wait, there was like one figure. Oh, hold on. That actually did work last. I just reminded me of something. You know, so yeah, last names basically come either from professions or from what happened to you. And there basically was like one guy who switched to the French side when Britain was fighting France, if I'm not mistaken, and his name literally fucking was John French. Homology, never heterology. Is that the reason why mathematicians lack of game? There's an official
There's an
algorithm called the
official algorithm
Cox-Zucker machine. Yeah, there's also the
Obviously.
the penis spectroscopy, if I'm not mistaken.
Proton enhanced nuclear induction spectroscopy.
Whoa! Don't
Wait,
look up penis spectroscopy. That's okay. CP spectroscopy.
No.
Okay. Oh, that one. Oh, thank fucking goodness the CP worked, because if the CP didn't work, that would be even worse than the penis. But yeah.
Spectroscopy is really weird. We just looked at things harder and it ended up working.
Spectroscopy is funny because like photon spectroscopy, or actually, I don't remember the exact, but spectroscopy literally is just looking. That's it.
But you can't tell me what material that is just by looking at it. Sorry, that was
nuclear double resonance.
See, the problem make it with naming everyone like John and whatever they invented is that you'd have to end up with John Spectra, and he needed to do like a lot of physics as well as at least 3 things in mathematics, which are all in different fields.
No, I like it. I like it.
John Spectra, the guy who invented optics. John Spectra, the guy who invented spectra in algebraic topology. John Spectra, the guy who invented the spectra of a ring. John Spectra.
No, I actually like it. I feel like it's
who did functional analysis and invented the spectrum of an operator.
I think it's great because then it just gets more confusing, and honestly that's just an additional upside. Like, you know, a couple generations down we have John Ion, who's a very famous mathematician, and like John and I don't know, John complex inner product complete metric space. Just took it a maiden name, of course.
Is the name given to you like after you get your PhD? Like after my PhD, am I going to end up like John Motivik and stable homotopy theory of K-localized spectra, whatever the fuck?
Whatever the fuck is obviously at the end added, yeah. Exactly. It's like with the popes, you know, when the pope becomes the pope, they pick a new name. The same thing should happen, in my opinion, for mathematicians.
My PhD student friend is going to end up John integrals and motives.
No, John Spectra is most famous
Because, like-
for being the father of the people who invented all those things. John Tumming was famous for his invention of quaternions. Do you think a single person gone to math after trying to look for hairy balls and accidentally running into algebraic topology? Statistically, not impossible. That's how I got here.
There are many ways of getting into algebraic topology. You can either you look up hairy balls. That's how most people end up here. No, but you know, or you're an algebraist in denial, and then you're me. John is famous for being the guy who just
It's John's.
John is the family name, like from the start. Like you're aware of that, right?
Actually, the entire time, John was the last name, you know. For John Topology, the first name is Topology, of course.
And the
John.
name's Topology.
John.
Topology.
Topology John. We went for the same bit, we just went for it in reverse. John is the guy. John is him.
I mean, like, to be fair, it would make it easier to curse exactly the right person at each time. Like,
Exactly.
You could stare at the ceiling, raise up your fist and say, "Damn you, John homology with local coefficients."
Or, you know what? Or just not to waste time, you just look up and be like, "Damn you, John!" Just end there, just in case, you know, every single one of them.
Yeah, but you insult your advisor, and I think they wouldn't be like... That may not jive with them if they're not into that.
Honestly, that's such a that goes so hard. Such great motivation. Basically, whenever something annoys you, just realize the fact that to that thing, at some point in history, someone named John probably contributed. So you can just yell at this guy, "Damn you, John!" It's gonna hit.
The only counterexample is John Goodenough, the inventor of lithium batteries.
I forgot that was a fucking thing. No, John good enough.
Let's see. Mathematicians named John. We have John Conway, John Nash, John Bayes, but he's actually a physicist. He does category theory, but he pretends he's a physicist. Okay, so apparently...
No, what did you find?
So I just found out
What did you
that
find out?
apparently there's a mathematician who was named John Norman... Fuck, I can't pronounce. He was named John Norman Nather. Straight up. We have John Math.
Oh, math. He
It's not
muffs.
a guy.
He muffs.
John Goodenough is a real guy. What? Yeah, it is. He is. Or
Yeah.
at least he was.
John good enough. Yeah. Actually, I don't think that's how that was spelled. I think it was good enough. But wait, how was it spelled actually?
Oh, it's spelled good enough, I think. John Goodenough, you know, the son of John Lithium and John Battery.
Famous for creating lithium batteries. John B. Goodenough. There we go. And he died 2 years ago at age 100, by the way. Damn. What a wild... He fucking invented RAM? Like piss away
What?
with the lithium ion. Known for random access memory. Also, I'm completely skipping over the good enough Kanamori rules, which is also hilarious. But I mean... You mean to tell me that RAM was... Which part of RAM did... Random... What? It's not like history. There's nothing that... John... What? John, how did you...
We
Developing
have John
random...
von Neumann, famous for creating von Neumann algebras and other stuff.
Have you heard of the John, by the way? The actor. Have you heard of him?
The John?
John Head, yeah.
John Hurt.
John Ireland. Fucking Canadian actor John Ireland.
John von Neumann is the John Euler of mathematics.
John Ireland is a powerful name for someone who's Canadian.
Oh yeah, John Napier. And we known for inventing like logarithms or whatever.
Have you heard of the legend of John Hertz? There's a new John Hertz every 100 years. Darn. Okay. Crickets.
No, it's funny. It's I laughed.
Busy looking for even more Johns. There's so many John Adams.
John Venn of Venn diagrams was also named John. John Wallis of the Wallis integral was also named John.
John Cone. John Doman. We found the John.
Wait, fuck, how am I so dumb? The guy who wrote the book I'm reading right now. John Milnor. Oh, and John Tate also. Of number theory fame. Anyways, I think I'm really going to go to like sleep.
Yeah,
or
I think that's
whatever.
enough Johns for today. I do agree. I
Yeah.
should probably go to. I'm really tired. There's an Irish John Canadian. Funny
But,
to
nice
know.
stream, everyone.
Alright, bye Robux. That
Bye,
was
everyone.
actually I'm
Bye,
so
chat.
bye. Average no American person finding out they have any ancestry from Ireland. That is painfully true though. Unfortunately. But anyway, I think that'll be it for today. I am also really sleepy tired. Finish the video, hey. That was something. Tomorrow we're gonna pick this up, probably work on the math video, and I suppose for now that'll be it. Thank you so much for watching, and have a great day.